So now I want to talk about composition of linear transformations, which is a little bit of a jump ahead, but I think it's good to do it now. Let's say that we'll say TA and TB be linear maps given by TA of some vector x is AX. So A is, some matrix. And TB of x equals BX for matrices AB. And we'll assume that the dimensions of A and B are such that the composition that I'm going to write is going to actually exist. But just for simplicity, we can say that everything is in, keep it simple, like two-dimensional space, n-dimensional space. All right, so you can say, let's just keep it simple, two-dimensional space. Let TA be R2 to R2. TB is also R2 to R2. Because the idea works similar in general. So how would I compose TA and TB? What is the matrix for TA composed with TB? So the way to think about this composition is, remember, TA composed with TB of x, I'm passing it into TB first and then passing the result of that into TA. So it's TA of TB of x. So this is just composition of functions here. So what's the matrix for this? Because the matrix for TA is A and the matrix for TB is B. How about for TA composed with TB? Well, on one hand, we can just sort of do it algebraically almost, right? TBX is BX, okay, so TA of BX. But TA of anything is just A times whatever that is. So this is just A times BX, which is ABX. Because matrix multiplication is associative. That's also a property of the matrix multiplication that can be proved, but that's very, it's just scut work. So now we know from this not terribly enlightening proof that the matrix for the composition is just the product of those matrices, the matrix multiplication by a matrix. But then what is that? What does it mean to multiply two matrices? So far in this little series, we've only done matrix times vector. What's matrix times matrix? Well, let's find out. Let's do it a little bit more of an intuitive way. So A, let's just make sure we're in R3 for now, keep it simple. We're going to have A11, A12, A13. Okay. There's A. And the way that we do the subscripts is the first number is the row, second number is the column. A12 is in first row, second column. Sometimes for short, we just call this, AIJ. It's just the matrix where the entries are A sub ij. All the same thing. And let's say B is the same thing. B11, B12, so on and so forth. So what do I want to happen with the composition? Well, remember, let's have the matrix for the composition here. Remember again, what do I want the first column to be? I want the first column to be where the first basis vector, 1, 0, 0, gets mapped to. So where is that going to get mapped to? Well, let's see. I have TA of TB of the vector in the x direction, the first one, 1, 0, 0. This thing is going to be the first column because it's where the composition sent the first basis vector, 1, 0, 0. But hold on a minute. What's TB of 1, 0, 0? That's just saying where did TB send the first basis vector? That's just the first column of TB, right? This thing here literally is where TB sends the first basis vector. This must be the first column of B. This is going to be TA times the first column of B, which will be, B11, B21, B31. Okay? I should put more parentheses there. But this is the first key idea here. In fact, I might as well just fill this out since it won't take too long. So what I'm going to do is, oh right, and of course, TA of anything is just A times that thing. That's how we define TA. That's going to be A times B11, B21, B31. Essentially, it's A times the first column of the matrix B. Okay? So let that sink in, but I'm just going to do the same thing again for the next column, just to really rub it in. So this here is going to be the first column of our matrix for the composition. I guess I'll do A, B11, B21, B31. And I like to put, this, you'll see, it makes things a little bigger. I like to put like a line like this, where it's saying whatever this matrix vector product is, which we know is going to be a vector, that's just going to be the first column. All right. There you go. That's the first column. So what's next? The second column is going to be where the composition sends the second basis vector, which in this case is going to be in the y direction, 0, 1, 0. But again, what is TB of 0, 1, 0? Well, just say what it is. It's TB and where it mapped the second basis vector. That's the second column of the matrix B by definition, right? This column, the second column of the matrix B is where it sent the second basis vector. So this down here would be TA of the second column of the matrix B, B12, B22, B32, which is just going to be A times that, B12, B22, B32. So the second column is going to be whatever that matrix vector product is. But I put these lines to show it's, it spans the whole column, whatever this matrix vector product is. That's the second column. And hopefully you can see, or you can do it all over again if you want to. The third column will be where A sends the last column of B. So this matrix, whatever it turns out to be, that's the matrix for TA composed with TB. All right then. So what is that? This is not particularly pretty. And it's not. And in fact, that's why we're about to define matrix-matrix multiplication. It's like these A's here, they're sort of like, you can imagine, I don't need to write it, 3 times. I could just maybe have this shorthand notation where I distribute the A out and I put it on the left outside. So this is like a notational definition here. This, I can just take this A that's in sort of part of calculating each column, just pull it outside in the front, on the left, since I'm multiplying on the left here. And then what's sort of left over it's just B1, 1, B2, and B3, 1. That's the first column of the matrix B. And this one second, and this one the third column of the matrix B. So this is a purely I guess I'm going to say this is a purely notational simplification. Just pull the A out and just say that we're going to call it to the same thing just to make it easier for us to write. Yeah, but guess what this is? That's just the matrix B. A, B. This is how we define matrix-matrix multiplication. Mainly just this right here. If you see the product of two matrices A, B, what you're really computing with all that dot product stuff is you're just computing this. You're just computing 3 separate matrix vector multiplications. And each vector is just each next column of, in this case, capital B. And this really hopefully does not come as too much of a surprise. Because if you have done matrix multiplication before, you're literally just doing this, If you have ever seen it before, if I were to do 1, 2, 3, 4, multiplied by, 3, 4, 5, 6, maybe one way that you were taught to do it is you do 3, 4, and then you sort of calculate that matrix vector. So you just sort of imagine that the 5, 6 isn't there. You just calculate this, and that's going to be the first column. So in this case, it's going to be what? 3 plus 8 is 11. 9 plus 16 should be 25. And then you sort of carve 3, 4, and you do it again with the second column, 5, 6, and then you do the same thing. And I won't calculate it because it's just doing math, but that's exactly what this is. I'm just taking the first matrix and multiplying it by each column of the second matrix in turn, and putting those as the respective columns of the matrix-matrix product, which is exactly what this is. The matrix in front, in this case A, times each consecutive column of the second matrix. And now we know the reason. It's because this is where the first basis vector gets sent under the transformation TA composed with TB. So this is one motivation behind how we define matrix-matrix multiplication. The process of it just being a bunch of sequential matrix vector multiplications embodies the fact that I am putting one transformation, taking the basis vectors and putting it through that one, and then taking the results of those through the next one. This is the putting it through the next one, putting it through A. That's composition.